Hello and welcome to this revision session for AQA A-Level Physics Paper 3, the Astrophysics option. So in this particular revision session we're going to look at answering examination questions on AQA A-Level Physics for the Astrophysics option. So if you've been successful and learnt in today's lesson, you should be able to answer A-Level Physics examination style questions and then assess your understanding on A-Level Physics and understand what topics you need to improve upon for AQA A-Level Physics. So how should you prepare for this revision session? When completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In the session, write down your working out and answers to the questions in the revision session. When doing this, make sure you write in full sentences and show your full working out. And in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So what tips should you have on revising for AQA A-Level Physics? Well, the first step is learning the key facts. Use the revision guides, class workbooks, prep notes, textbooks to learn the knowledge and the key ideas of the course. You might want to write mind maps or write out notes yourself. The second step is to test yourself. Use Caboodle, use Seneca, use the student knowledge checker to quickly test your own knowledge and retrieve it from your understanding. And you may wish to use cue cards to do this. And then finally, step 3, use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. And you may wish to download past papers to do this. So your steps of learn the key facts, then testing yourself and practicing exam style questions are how you should revise AQA A-Level Physics. So let's now practice some questions from the Astrophysics option based on the 2022 Advanced Exam Information. So the first question says, Table 2 shows some properties of the 4 brightest stars in the constellation Canis Minor. We discuss with reference to the Apoca Scale why many star maps show only 2 stars in the constellation Canis Minor. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important that you know what the Apoca Scale represents, which is linked to apparent magnitude, and that Hipparchus had the brightest stars at 1 and the dimmest stars at 6, because this is the conditions with the naked eye that he could observe. So the note is that Gamma A and HD 66141 are much dimmer than the 2 brightest stars, and therefore not much brighter than magnitude 6, so therefore only 2 stars, Gamma Cae and Procyon, are likely to be seen unless you got really good conditions in the night sky, because Gamma and HD have apparent magnitudes close to the dimmest that could be observed. The next question says, calculate the distance from the Earth to Procyon and give an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, you've got to use your equation apparent magnitude minus absolute magnitude equals 5 log d over 10, where d is given in parsecs. So you've got small m, which is the apparent magnitude, and you've got big M, which is the absolute magnitude. So you pop your values into your equation and you rearrange it to make log d over 10 the subject. And at that point, you can then work it through and you get d is equal to 3.45, and you've always got to give your distance with this equation in parsecs, so that is the unit to use. The next question says, if you look, table 3 contains information about 2 galaxies, NGC 396 and NGC 3379. Discuss whether this data is consistent with Hubble's law. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you prove if something is consistent with Hubble's law? Well, we know with Hubble's law that we can say that with our equation that we can use that you could do h is equal to z over d, for example, or you could also say that v is equal to hd, where h is the Hubble's constant and d is the distance. So if we're trying to show that Hubble's law is consistent, well, what we can therefore do is work out the values of h, the Hubble constant, for both of the galaxies and then lead to a conclusion. So if we said that v is is going to be equal to HD, well then H is equal to V over D. Now you might think we've got D, but how do we work out V? Well, we can work out V by using the redshift equation. So we know from the redshift equation that Z is going to be equal to V over C. So therefore we can work out what V is by doing Z times by C. So we can work out the value of V for both of the particular galaxies. So by doing your redshift factor Z times by C, 3 times 10 to the 8. Now it's important to note that when we're working out our consistent value for the Hubble constant, which is H, we've got to convert our value of velocity from meters per second, which you've worked out in that previous equation, into kilometers per second. So you convert both of them. Then at that point you will then work out the Hubble constant for both. Now in this particular example you should work out that the Hubble constant for NGC 936 is about 69. So that is consistent with the value given in the data book, firstly, which shows that it links to that. Now please do note that when you're doing this equation and working out the value of the Hubble constant by saying, well, if V is equal to HD, well then H is equal to V over D, D has to be given in megaparsecs. Now in this particular table you're given your value of distance in light years, so you're going to have to convert your light years into parsecs and then convert your so your light years, your light years into parsecs and then your parsecs into megaparsecs. Now remember that there are 3.26 light years in 1 parsec and there are 10 to the 6 parsecs in 1 megaparsec. So that allows you to convert your value from light years into megaparsecs. Now when you work it out for NGC 3379, you'll notice that the Hubble constant is 92 kilometers per second per megaparsec. Now that then leads to 2 conclusions you can make. Firstly, NGC 3379 has a value which is very far away from the Hubble constant value given to you in the data booklet, and the 2 values are not consistent with each other, indicating that you can say that possibly NGC 936 verifies Hubble's law, but definitely both of them together do not. The next question says, quasars are the most distant measurable objects. Discuss one problem associated with the determination of the distance from the Earth to a quasar. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, it's the idea that distant quasars are very, very faint. Now that's an important idea because with reference to the inverse square law, the idea because they're they're very, very faint, it's very difficult to observe them, and the reason why they're very faint is because they are very, very distant. Now in addition, we could also say that when we're determining the distance, we're not actually considering the acceleration of the universe, which has taken place when we use to work out far distances, like by using the inverse square law. We're assuming that the expansion of the universe has been constant. The expansion of the universe has not been constant. We think it is accelerating due to dark energy powering this acceleration of the expansion. In addition, you could also say that this could also lead to Hubble's law or the inverse square law not being reliable over large distances due to that acceleration due to dark energy. The next question said, an astrophysicist has to decide whether to use a reflecting telescope or a refracting telescope on a spacecraft. Discuss which type of telescope to use. So this question is asking you to pretty much look at the advantages and disadvantages of reflecting and refracting telescopes and come up with a conclusion. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you do this? You've got to make a couple of clear comparisons. Now, it's probably the easiest way is to talk about the problems of each type of telescope. So with refracting telescopes, they can suffer both spherical aberration and chromatic aberration. So chromatic aberration occurs when radiation is refracted through a lens, while spherical aberration occurs when the radiation has to be reflected off a mirror, which will happen in a refracting telescope because there will be a mirror there as well. Now, also you'll indicate that reflecting telescopes are going to be lighter and going to be shorter than your refracting telescopes. That's an issue in constructing a refracting telescope to be large enough to detect images that you want to see, and also the idea that the mirrors don't have that chromatic aberration as opposed to the refractors that do. But the issue with reflectors is that your secondary mirror in your Cassegrain arrangement for your reflecting telescope will block some of the light out, so it will reduce your image brightness, making it hard to see. And also you've got the idea of the fact that that when you've got your Cassegrain arrangement for your reflecting telescope, you'll also get a little bit of diffraction as well as the radiation goes past that secondary mirror. Now the next question says, Table 1 summarises some of the information about 4 stars in the constellation Cassiopeia. So firstly, state which star in Table 1 is the dimmest on the absolute magnitude scale, and then calculate the absolute magnitude of Cedar. So pause the video now, then unpause the video when you want to go through your answer. Right, so to work out how absolute magnitude works, the idea is that the lower the value of absolute magnitude, okay, is going to give you the brighter star. So what you would have to do is you would look on here and you look at the apparent magnitudes and you look at the distances from each one. Now they've all got very similar apparent magnitudes, but the distance is a lot different between them. So you can see that you've got the idea of Cedar here having a distance of 228 light years, okay, as a result. So your value is going to, if you're looking through, Tishish as well it's got a small absolute apparent magnitude but then a very large distance. Now Kapap here has the smallest distance and therefore, but also the smallest apparent magnitude, so therefore it's most likely to be the dimmest because they've all got a similar brightness in the Earth's atmosphere, but Kaf is the one which is the closest to us, indicating that when all things are equal with the absolute magnitude scale, it's going to be the dimmest one. Now, how do you calculate the absolute magnitude of Cedar? Well, once again, you've got to use your equation of small m minus big M equals 5 log d over 10, where d is given to us in parsecs. So you've got to make sure that your distance is correct here. So it's going so your distance is given to you in light years in the table. So you've then got to convert it into parsecs for our equation. Remember, this equation always requires distance to be in parsecs. So remember, there are 3.26 light years in a parsec. So you divide your value given on the table, which is 228, by 3.26 to get your value of distance to be 70. You've got your apparent magnitude. You can work it all through, make big M the subject, and you get your value out to be minus 2.0, which means it's an extremely bright star because it's a negative value. The next question says, type 1a supernova can be used as standard candles. State what is meant by a standard candle, and then secondly, sketch on figure 2 the light curve for a type 1a supernova. Annotate your graph with suitable scales and a unit for time. So pause the video now, then unpause the video when you want to go through your answer. Right, so the standard candle definition is just a clear definition you've got to learn. A standard candle is a astronomical object which has a known absolute magnitude and a measurable apparent magnitude. Now you've got to also be able to sketch the light curve for a type 1a supernova. Now you can see here our values on our absolute magnitude on the y-axis and our time in distance given on the x-axis. Now the important things to note are that the peak of a type 1a supernova is about minus 19 on the absolute magnitude scale, and it occurs approximately about 10 days after the start of the process. Now you should have a graph from about 40 days to about 500 days, with the peak occurring at about 10 or 20 days after zero, and it going down to a lesser value after about 300-400 days. The next question says, measurements of a type 1a supernova are used to find a value for the Hubble constant. The distance from Earth is known for many type 1a supernovae. Describe how these values of distance are used and with other data to find the Hubble constant. Your answer should include the other data needed and how this data is used, the graph plotted and including appropriate units for the axis, and how the Hubble constant obtained and any limitations on the result. So pause the video now, then unpause the video when you want to go through your answer. Right, so with this one, you've got to answer each bullet point separately. That's a key point for A-level physics questions. Always answer each bullet point separately. So how can we look at the data? So the first thing to note is that you need the value for Z, the redshift value. So therefore you can use Z to find out what your value for velocity is, the recession velocity of that particular object, because we know that Z is equal to V over C. So therefore the recession velocity V is equal to Z times by C. And we can also measure the wavelength of spectral lines to help us obtain this as well, because we can say Z is equal to the change in wavelength due to redshift over the wavelength of the element in a reference point. Now once you've then worked out your value of Z, and then use that to derive your value of v. Well, therefore we can plot on a graph the velocity on the y-axis and the distance away from us on the x-axis. Now, because we want to work out the Hubble constant, well, velocity has to be given in kilometers per second, whilst distance has to be given in megaparsecs. Those are just the standard values we use to determine the Hubble constant. So when we plot v against d on the graph and have our nice straight line, the gradient of the graph is going to be the Hubble constant. Now, there are issues with this particular value that you'll gain. So the idea is that the value of apparent magnitude is very much affected observationally by what materials it passes through between when it's been emitted by an object and when it's got to us in the Earth's atmosphere. Now, as well, with the values from many distant galaxies, you'll notice that there are a massive variation in data. So therefore, it's very difficult to draw a straight line through the origin to derive your gradient. So that's a big area of discussion, and we also need lots of data to do this accurately, and we just don't have that. There's just not been enough observations to get lots and lots of data to ensure we get an accurate gradient. And finally, we also need to consider that Hubble's law indicates that the Hubble constant should be constant, as the name suggests, indicating the expansion of the universe has been constant. We now believe the expansion of the universe is not constant, rather it's accelerating due to dark energy, so that's another limitation on the value that you derive. The next question says, which graph shows the light curve for type 1a supernovae? So pause the video now, then unpause the video when you want to go through your answer. As mentioned before, the key factors for the type 1a light curve for type 1a supernova is that you get an absolute magnitude peak at about -19, and that happens about 10 days after the actual supernovae, and it then tails off for the next 300-400 days. Now, the only one that shows this for us is the answer of D. Now, the next question says the Andromeda Galaxy is approximately 7.7 times 10 to the 5 parsecs from the Earth. Deduce whether a type 1a supernova which occurred in Andromeda can be observed from the Earth with the naked eye. So pause the video now, and then unpause the video when you want to go through your answer. Right here, you've got to link it to the Apoca Scale. And the Apoca Scale is that the dimmest object a human can see with the naked eye has an apparent magnitude of 6. So we use our equation small m minus big M equals 5 log d over 10. Now we rearrange this to make small m the apparent magnitude, the subject. Now we'll also make sure we've got to turn d, our distance, into parsecs. Well, sorry, it's already given in parsecs, so we're fine with that. It's 7.7 times 10 to the 4. So you work it all through and you get your apparent magnitude to be plus 5.1. Now that is brighter than the limit, which is 6, because remember, the smaller the number on the apparent magnitude scale, the brighter it is. So therefore you are likely to see it with the naked eye on the Earth. The next question says IC2497 is a galaxy that contained a quasar. It's believed that the quasar stopped emitting radiation several thousand years ago. Suggests why the quasar stopped emitting radiation, and IC2497 has a redshift of 0.0516. Determine the distance from the Earth to IC2497. Give an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to understand why quasars emit radiation. So quasars emit radiation because quasars are formed around black holes. Now, obviously nothing can escape a black hole, no radiation can escape, but as matter is being drawn into a black hole, before it passes the event horizon, it can emit radiation because it's being pulled in and accelerated towards the black hole. So that particular process releases radiation, and so this tells us that if it's no longer releasing radiation, that no matter is being drawn into the black hole. Now the next question is asking us to work out the distance after being given a value of the redshift. So like in previous questions, you've got to use two equations. You've got to use firstly the equation z equals v over c to work out our value for v. So we say v is equal to z times by c, c being the speed of light and z being the redshift value given in the question. So you get 1.55 times 10 to the 7 meters per second. That can therefore be converted into kilometers per second. Now we do that because the Hubble constant equation requires the velocity to be in kilometers per second and the distance to be in megaparsecs. So therefore we say if v equals hd, d is equal to v over h, where h is the Hubble constant and is 65 kilometers per second per megaparsec. We've just worked out our value of v is 1.55 times 10 to the 4 kilometers per second. So you work our answer out to be 238 megaparsecs. The next question says, a convergent lens of focal length 0.15 meters is used as the eyepiece of an astronomical refracting telescope. In normal adjustment, the angular magnification of the telescope is 5.0. Calculate the distance between the eyepiece lens and the objective lens of the telescope. A student measures the focal length of the eyepiece lens. She uses it to form an inverted magnified image of a real object. State one other property of the image formed by the lens, and the image is formed 0.60 meters from the lens. Calculate the object distance. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one we've got to remember our equation. Magnification is equal to the focal length of the objective over focal length of the eyepiece. Now we know that magnification is 5 and the focal length of the eyepiece lens, which is told in the question, is 0.15. So we can rearrange that to get our focal length, our focal length of the objective to be 0.75 meters. Now at that point the total length of the telescope is the two focal lengths of the individual lenses added up. So it's 0.75 plus 0.15, which is 0.90. Now if you think about it, what's another property of the image formed by the lens when you've got an inverted magnified image? Well, you've got to be aware that it's going to also be a real image because it will be captured on a screen. Now in our last question, you've got to use our equation. 1 over focal length is equal to 1 over the object distance plus 1 over the image distance. Now we've got our different values. We've got our focal length from the question. It's told us to be 0.15 from the top. We've got our object distance as told us in the question, 0.60 meters. The image distance, because the image is formed 0.60 meters from the lens. It tells us that in the question. So we can work out 1 over u. So when we work it through, we get our answer to be 0.2 meters. The next question says, draw a labelled ray diagram to show how an image is formed on an astronomical refracting telescope, and further analysis of the lens reveals that the value of its focal length depends on the wavelength of the light used. What is the name given to the image problem that shows you the variation of focal length? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, when you're drawing your image for your refracting telescope, remember that when you draw your construction rays in, you're going to have 3 non-axial rays going through, and then it'll go through the first lens, then it'll go through the second lens. You've got to draw your images in. Remember, if they're in normal adjustment, the focal plane for both the eyepiece lens, okay, and the other lens is going to be in the same plane. That's the definition of normal adjustment. So make sure you can draw it in, and you should be getting a magnified inverted image out of that second lens, so you can work it through like that. Now again, what is the name given to the image problem associated with the variation of focal length? Now that occurs because you've got radiation with different wavelengths or different colours, which is going to be your chromatic aberration. Chromatic meaning colour, aberration meaning the blur. The next question says, Table 3 summarises some of the properties of 3 stars in the constellation Aries. Hamal is 66 light years from the Earth. Calculate the absolute magnitude of Hamal. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this question, once again, we use small m minus big M equals 5 log d over 10, where d has to be in parsecs. That's a condition of the equation. Now, we can work it out because we've got the 66 light years from the Earth. Now, there are 3.26 light years in 1 parsec, so you do 66 over 3.26 to get yourself 20 parsecs. We can then sub that in the equation, and we've got small m apparent magnitude from our table. We then use this and work out big M, which is 0.5, the absolute magnitude. Now the next question says, state which property of the first identified quasar led to its discovery. Then 3C48 is a quasar in the constellation Triangulum. It is believed to have a power output 4 times 10 to the 11 times greater than that of the Sun. At the Earth, the Sun's intensity is 1.4 times 10 to the 17 times greater than that of the quasar. Calculate using the inverse square law the distance from the Earth to this quasar in AU. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's important to know that we observe quasars because they are a very bright radio source. It's not good enough to just say they are a radio source, it's that they are a very, very, very bright, intense, powerful radio source. Now, in this next question, you're going to have to use the inverse square law and link the power output of the quasar to the power output of the Sun. So what you would say is that that you're going to say the intensity is equal to the power over the distance squared. Now, you know straight away that the power of the sun is going to be equated to 1, and the power of the quasar is equated to 4 times 10 to the 11, because you know the power of the sun is 4 times 10 to the 11 times less than that of the quasar. It tells us that in the question. Now, we also know that the intensity, though, at the Earth of the sun is 1.4 times 10 to 17 times greater than that of the quasar. So we've got to put an additional factor when we're looking at the power of our quasar to be that of 1.4 times 10 to 17. So we can say that the power of the sun is therefore going to be equal to, its power of the sun is equal to the power of the quasar times by 1.4 times 10 to the 17, because you know that the quasar has to have that factor multiplied in there to get them equal to each other, given from the question. So we can say the power of the sun over 1 squared, because we're looking at the distance from the sun to the earth, which is 1 AU, is equal to 1.4 times 10 to the 17, this additional factor to equate the two to each other because of the difference in the intensities, times by 4 times 10 to the 11, times by the power of the sun over the distance from the quasar to the earth squared. We can then rearrange it all out. Remember, the power of the sun can just cancel through because we're just equating it to 1. So therefore we can say distance squared equals 4 times 10 to the 11 times by 1.4 times 10 to the 17. So therefore d squared is equal to 5.6 times 10 to the 18. So d equals 2.4 times 10 to the 14, and the units are AU because the distance from the earth to the sun was given in units of AU. So the distance from the quasar to the earth must also be in that particular unit. The next question says, Table 1 summarizes some of the properties of Ceres, the largest object in the asteroid belt between Mars and Jupiter. So calculate the closest possible distance in meters between Earth and Ceres. Now calculate the angle in radians subtended by Ceres to an observer on the Earth when Ceres is at this distance. Give your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, look at how calculate the largest possible distance. So when you calculate the largest possible distance, it's going to be 2.56, the largest possible distance, minus 1, okay, which is the distance between the distance between the Earth and the Sun. So you can work it through like that because we're looking at the distance between the Earth and Ceres. So we'll find the distance from the Sun and Ceres in the table, and then saying the distance between the Sun and the Earth is 1. So therefore we can work out that the distance between the Earth and Ceres is 1.56 AU. We can then convert from AU to meters by saying 1 AU is 1.5 times 10 to the 11 meters. That conversion factor is given to you in your equation book. So therefore the value is 2.34 times 10 to the 11 meters. Now in this next one we can do a bit of trigonometry here and say the angle is equal to S over R, where R is going to be equal to the distance between the two objects, which is between the Earth and Ceres, and S is going to be the actual diameter of Ceres. So we know that the diameter of Ceres from the table is 9.5 times 10 to the 5. Divide that by the distance between Ceres and Earth. We just worked on the previous question to be 2.34 times 10 to the 11 meters. So we get our angle in radians to be 3.12 times 10 to the minus 6 radians. Please always remember that we can use this equation to work out angles in radians because of the small angle approximation. So I hope you've enjoyed this particular revision session on AQA A-level physics in the astrophysics option. If you've been successful and learned in this revision session, you should be able to answer A-level physics examination style questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for AQA A-level physics. So thank you very much for watching this particular revision session on AQA A-level physics paper 3 astrophysics. Thank you very much and have a lovely day.